Hi, everybody. This is Dr. Nigro with the Physics Fundamentals Screencast. This is a second in my series dealing with work and energy. This one is specifically going to look at when we apply a constant force, but the object is moving up or down an inclined plane. All right, I wanted to pull this specific problem type out separately just because it's a little tricky because you have an incline angle and then you also have this angle theta in your work formula, and sometimes it can get a little confusing. All right, so just as a reminder, when you have an object on an inclined plane, you're going to have FG pointing directly down, and then opposite, you'll have your normal force, but they don't point directly opposite one another. The normal force is always perpendicular to the surface, so it's not directly across from FG this time, which means that I need to split that gravitational force into its X and Y components. So you can see here's my Y component, and then here is my X component. All right. Now, for this first one, I'm going to assume that the object is sliding down my plane, which means that the motion will be here. Right, actually, I'll make that a little shorter. You'll see why. All right, so here's my motion. All right, so in this upper corner, I'm going to draw my free body force diagram. All right, so I have my normal force, that support force, and then equal and opposite is not Fg alone, it's Fgy component, and those will be equal and opposite. Now, because of the direction of that Fgx component, it's going to be to the left, Fgx. And because I have friction present, friction opposes the direction of motion. All right, so if motion is down, then friction is this way. All right, so that means I'm going to have a frictional force to the right. Okay, so this is what my free body force diagram looks like. And then I could write my F-net equations, and then I could use those to find these values. All right, but one thing I want to point out is, what does this free body force diagram mean in terms of our theta value for our work formula? All right, so remember, the work done on an object is equal to the absolute value of a particular force times the absolute value of the displacement times the cosine of theta. All right, and theta is the angle between the force and the motion. All right, so the motion here is parallel to the surface of the inclined plane, up and down. All right, so in this particular case, when we're sliding down, all right, when that motion is down the plane, all right, then we're going to have our theta for our gravitational X component is going to be equal to 0 degrees because it's in the plane. It's parallel to the motion. All right, so that means that that FGX value, when it comes to, or sorry, the work done by that FGX value is going to be positive because the cosine of 0 is 1. All right, the theta for our frictional force is going to be 180 degrees because that is exactly opposite of the motion, which means we're going to get a cosine of 180 equal to -1, so our work value here will be negative. All right, so FGX is actually adding energy in to help with the motion of the object, whereas the frictional force is removing it and trying to slow it down. Okay, so that's when the object is sliding down. All right, what about when the object is moving up? All right, so we're going to have a similar set of forces. Whoa, that was a little crazy. Sorry about that. All right, we've got our force of gravity straight down, our normal force perpendicular to the surface. We split that into X and Y components. Whoops, X. All right, this time our motion is going to be this way. So here's our motion. All right, so if we think about our free body force diagram again, not much has changed. We still have our normal force up. Equal and opposite is that Y component of gravity. And we still have our X component of gravity off to the left, pointed down the plane. The difference this time is, where is friction? So if motion is up the ramp, then friction opposes motion. So friction is going to be down, which means I need to add it. Oh, I didn't give myself very much room. Let me add it in here. All right, so here's FGX. Also to the left side along with FGX. So you can see the difference between my two free body force diagrams. All right, and that's going to influence the sign of work for these. All right, so when we have motion up the plane, all right, the theta for our x component this time is 180 degrees. All right, so that means that we're going to get a cosine value of -1, so our work value is going to be negative. All right, our theta value for our frictional piece also will be 180 degrees, which means again we'll get a negative work value. All right, so in this situation where the object's trying to go up that inclined plane, it's got to work against both the gravitational x component and the frictional force. So this is why back when we were doing forces, you find that the acceleration as the object moves up the plane is actually greater than the acceleration as it goes down, which seems like it should be the opposite, but it's because as the object slides up the plane, friction and the x component of gravity work together. So we get a bigger acceleration value, whereas when it's sliding down, they work against each other. So we get a smaller value. But then both of those situations also play into our work values. We're going to get positive work for FGX if it's sliding down and negative work for FGX if it's sliding up. All right, you'll notice that the frictional force is negative in both situations, which makes sense because it's working against the motion. Okay, so let's try a couple problems. All right, we have a block, 6 kilograms, that starts from rest at the top of a ramp with an incline of 30 degrees. If the block slides down the entire ramp, 15 meters, how much work is done by the applied force? Assume no friction. Okay, so I'm going to start with a free body force diagram. All right, so I've got a block. All right, I know that I've got the normal force up. I've got that y component down. Those two are equal and opposite. And I know that pointing down the plane is my x component of gravity. And that's it. It says no friction, so I don't have to do anything else. Now, the applied force. So we are used to an applied force being a push or a pull that we indicate, that we put into it. All right, but an applied force actually could be any other type of force that is causing the motion. All right, we saw that with our hanger and cart labs, that the gravitational pull on that hanger is what actually was applying the force and causing the motion. Same thing here. All right, the x component of our gravitational force is what is causing that block to slide down the plane. So that is, in fact, our applied force. All right, so when we're asked about the applied force, what we're looking at is FGX. All right, so let's list what we know. All right, I can calculate FG. I have a mass of 6 kilograms, so that's going to be 60 newtons. All right, I have a displacement of 15 meters down that ramp. All right, I have an incline angle of 30 degrees. All right, and then I have a work angle of 0 degrees. So that's going to go in my work formula. And then the question is, well, what is the work that my force is doing here? Okay, so I know that the work done by my applied force is going to be equal to the absolute value of that applied force times the absolute value of the displacement times the cosine of my angle between the motion and the force. Okay, so I need to calculate FGX. All right, so I'm just going to do it right in here. So FGX is going to be FG times, and this is an inclined plane problem, so the sine of my 30-degree incline angle times my 15 meters times the cosine of my angle between the motion and the force. Oh wait, I forgot to put in FG. Oops. 60 newtons, okay? All right, so if I take 60 newtons times the sine of 30, and then multiply it by 15, and then the cosine of 0, which I know is 1, all right, then I'm going to find that I'm doing 367.5 joules worth of work here. All right, now I could have done the calculation for FGX off to the side and then plug that value in, but for me it was just as easy just to put it in. But you do it how it works best for you. All right, so let's look down at part B. Same block, same ramp. This time, friction is present. The kinetic coefficient of friction is 0.25. If the block slides down the entire ramp, how much work is being done by the frictional force? And then what is the net work that's being done? All right, so this time I need to find the work due to friction. So that's going to be equal to my frictional force times displacement times the cosine of the angle between the motion and this particular force. All right, so let's think about that frictional force. I know that's equal to my kinetic coefficient times the normal force. All right, and if I look up at my free body force diagram, I know that normal force is equal to the y component of gravity. So that means 0.2, and then I'm going to have Fg, which is 60 newtons, times the cosine of my incline angle, which was 30 degrees. All right, so 0.2 times 60 times the cosine of 30, and I'm going to have a frictional force of 13.6 newtons. All right, now you can say, well, that should be negative, and it should, but we're going to plug it in as an absolute value because that's what the formula is asking us to do. All right, so I'm going to say 13.6 newtons. All right, my displacement is the ramp, which is 15 meters, and then the cosine of 180 degrees. All right, remember, the theta value in our work formula is the angle between the force that we're talking about and the motion. And friction always opposes motion, so it's 180 degrees away from the motion. So that's why it goes in as a cosine of 80. All right, so the work that's being done by friction calculates to be negative 204 joules. All right, so that's the work done by friction. So that's this question. But the second one wants to know, well, what is the net amount of work that's being done on the block? So we're going to go back and think about that applied work we just calculated, and we're going to use it along with our frictional work to calculate our net work. All right, so we had an applied work of 367.5, nope, not newtons, joules, plus a negative 204 joules for friction. We plug that in our calculator, and we have a net amount of work of 163.6 joules. All right, so you can see how once we calculate the frictional part, it's negative work because it's opposing motion. And when that goes into our W net, it ends up pulling energy out of our system despite all the energy we're trying to put in. Okay? All right, so let's try this last one. This one's also two pieces. All right, this one we're going to go up the ramp instead. So we have a block, again, 8 kilograms this time, starts from rest, and is pushed 20 meters up a ramp with a force of 100 newtons. The ramp has an incline of 25 degrees. All right, so for part A, the ramp is frictionless. What is the net work that's done? All right, so free body force diagram time. All right, here's our box. All right, again, we know that normal force is up. The y component of gravity is down, equal and opposite. I know that the x component is to the left. Now this time it says pushed up the ramp. So we're going to have an applied force that is separate from that gravitational force. All right, and we're going to see what those two are in relation to each other because we're going to try to find that net work. All right, so in other words, F net for our parallel motion is going to be equal to Fg x component plus that applied force. Okay? All right, so let's list what we know. Again, I can calculate the gravitational force. It's 80 newtons. All right, I know that my displacement is 20 meters. All right, I have an incline angle of 25 degrees. And now, because I have two different forces, I'm going to have to wait about my angle between the motion and the force because it's going to depend on what force I'm talking about. All right, so I'm going to do a little pre-calculation. So I'm going to calculate this x component first. All right, so that's going to be xg times the sine of our angle. All right, so that's going to equal 80 newtons times the sine of 25 degrees. So if I plug all that in, I get an Fg value of 33.8 newtons. All right. All right, now I'm going to go to my F net equation. All right, so that net force is equal to my applied force plus that FGX. All right, so my applied force is 100 newtons plus a negative 33.8 newtons. All right, negative because it is going down the ramp. All right, so I plug those two values in and I have a net force of 66.2 newtons. All right, with that, I can calculate the net work. So that net work is going to be equal to absolute value of F net, absolute value of the displacement, and then the cosine of the angle between the two. All right, now cosine here is going to be F net's direction versus the motion. All right, and these, I've got a positive value for F net. The motion is in the positive direction, so we're going to get a 0 there. All right, so we plug in 66.2 newtons times 20 meters, I'm running out of space, times the cosine of 0 degrees, that's a 1. And I find that the net work that's being done here is 1,324 joules. Okay? All right, last part. If friction is present, and we get a kinetic mu value, what is the net work being done on the block? All right, so we know what the work is being done. In the absence of friction, now we need to put friction in. All right, so that force due to friction is equal to our kinetic coefficient times our normal force. All right, and remember that normal force is equal to that y component of gravity. All right, so we're going to get 0.2 for our mu value, and then FGY, we're going to have 80 newtons times the cosine of our incline angle, 25 degrees. Plug that in, and we have friction providing 14.5 newtons worth of force. Okay, now let's talk a little bit about our F net equation now. All right, so we've got FGX, we've got our applied force, but now we also are going to add in a frictional force on that left side. All right, it goes to the left because the object is trying to move to the right and friction opposes that, so that's why it goes there. So our net force is going to be equal to a negative 33.8 newtons. We calculated that before, and it's negative again because it's going opposite of our motion down that plane. All right, then we're going to add in our applied force of 100 newtons, and then finally our frictional force of negative 14.5 newtons. Again, negative because it's pointing down that plane. All right, add everything up. We have a net force of 19.3 newtons. So you can see that that frictional force is helping the FGX to drag, or at least slow it down as it tries to go up the plane. We end with our net work. Well, that's not what that says. There we go. We use our net force times our displacement times the cosine of theta. All right, and again, this value is positive, so it's parallel to the motion at 0 degrees. All right, so we're going to have a value of 19.3 newtons times 20 meters times the cosine of 0 degrees. So that cosine becomes 1. And we find that we have 386 joules of energy that's being used to help with the motion. All right, if you compare that answer to A, you can see we've lost quite a bit of our energy that we did have before friction showed up. Once friction showed up, then it's going to chew up or at least remove some of the energy we were applying. And this is where we end up. Okay? All right, so if you have any questions, please let me know. Remember, it's really important that you pay attention to what's going on in terms of up or down the ramp.